I have a little video to make today, and today I really wish I had my students here that could see, because I used to ask the question, when are we ever going to use this whenever I present something in class? Well, today I'm going to use something that I presented in class every year for 20 years, and it's finding the center of mass of a flat object. There's a way to do it experimentally, and it has to do with using the concept of torque. So let me talk about that idea of torque. Here I have a little ruler, and I'm supporting the ruler at its middle point here. I could even do it like this, would probably work just as well. And well, the question is, what do we have to do to get the ruler to start rotating? Now, if you might remember, Newton's laws say that if you want something to start moving or stop moving or change its motion some way, you have to apply a force to it. Well, for a macroscopic object like this, if you want something to start rotating or stop rotating or to change its rotational motion, then you don't need a force, you need a torque. Because a force isn't sufficient. You actually have to have what's called a torque. Let me see if I can show you an example of a force that provides a torque and one that doesn't provide a torque. Here is the ruler, and I'm going to apply a force to it. And it should be level on here, but the ruler's not perfectly balanced, I suppose. That doesn't really matter for our purposes. I'm going to apply a force perpendicular to the line from where the ruler can rotate. So the ruler can rotate about this little axis right here. And a line from there to where I'm going to apply the force would go this way. And I'm going to apply a force perpendicular to that line. And watch what happens. That's because that provided a torque, and that torque caused the ruler to start to rotate. It changed its rotational motion. However, I can apply the same amount of force this way. I'm pulling on the ruler now, and the ruler is not rotating because the force is being applied parallel to that line. So the line from where the ruler can rotate to where I'm applying the force, if I'm applying the force parallel to that same line, no torque is produced until the ruler does not start to rotate. We're going to use that idea to try to find the center of mass of a rigid object. Now, the center of mass are also called the center of gravity. Same thing for our purposes here because we're talking about small objects. The center of gravity is where all of the gravity that is acting on a rigid object can be said to act. You don't have to worry about the fact that every single atom in a rigid object is being attracted, is being pulled by the force of gravity. All you have to worry about is finding the center of gravity, which, as I said, is for our purposes the same as the center of mass. If you find the center of mass, then you can find the place where all the gravity would act on that thing. And here's how we're going to find it. The rigid object that I'm going to do is this beautiful sculpture my wife purchased a few years ago over in Fredericksburg, I believe. This little rigid object, we're trying to hang it so that it hangs vertically. It's the shape of the state of Texas, as you can see. And so in other words, what we want to do is when we hang it from a single point, when we're hanging it from that point, we want it not to rotate. So in other words, we want to support it in such a way that the center of gravity, which is the only other force acting on our object after we hang it up, only other external force that's acting on our object after we hang it up besides the place we're hanging it itself. If we can find the center of gravity, then we can just make sure that our point where we're hanging it is in line with the center of gravity. So if the center of gravity were right here, let us say, then if we support it up here, we know that it won't rotate if the force of gravity, the external force, is acting along the line of from where our object could rotate at that pivot there to where the force is acting. The force is going to act at the center of gravity. So as long as that center of gravity is in line with where we're supporting it, it's not going to rotate. The thing is, we got to make sure that that point then is in line with it when our object is the correct shape. We know that this line right here in the panhandle, that should be going horizontally. So we want to make sure that that's horizontal when we're supporting it. So we got to support it above the center of mass so that when we have it hanging on the wall, the line from where we're supporting it to where the center of gravity is straight down. Because the force of gravity always acts straight down, so we know that the line from our support point to the center of gravity, which is where the force acts, will be in line with the force of gravity itself. So to do that, we use an ancient technique. Appropriately enough, I'm going to use a modern recreation of a medieval astrological device. It has astrological symbols on it. Basically, it's just a calendar. But it's a calendar that is in the shape of a little pendulum here. And what that shows us is the direction of gravity. The direction of gravity, this is called a plumb bob, really, that's what the name of it is, points straight down. When you hold up a weight from a support point, the line of your pendulum here points straight down, because that's the direction that gravity pulls. So what we're going to do is we're going to pick a point on our object, some arbitrary point here, and I'm going to support the object from that point, and then I'm going to have, at that same point, I'm going to hold my little pendulum here. Now, this line right here is the line that gravity acts along, straight down. So somewhere along that line is where the center of mass must be, because this thing is not rotating. Because it's not rotating, we know that the line from the support point to the center of gravity, where gravity acts, must be in line with this rope, because this rope is acting where the force of gravity pulls. So somewhere along this line right here must be the center of gravity. And my wife is going to take a piece of painter's tape and line up the painter's tape along the back of this. We don't have to. There's a beautiful Bible verse in the back here, so I don't want to write on it. Normally in my class, I would write on it with a marking marker, erasable marker. But if you would just line up like one edge of that piece with the, yeah, like that. That's perfect. So somewhere along the left edge, from our point of view, of that tape should be the center of gravity. Now what I'm going to do is I'm going to support it from a different point. We'll point it from here. And so now, again, the rope is pointing in the direction that gravity is pulling. And so the line from my pivot point right here, since the state of Texas is not rotating right here, the line from my pivot point to the center of gravity and the line that gravity takes, which is what the plumb bob is showing us, must be along the same line. So therefore, the center of gravity must also be along this line. What we need to do is find the intersection of those two lines. There you go. So that intersection right there, the inside right here, that is where those two lines intersect. That means that that is the center of gravity, because that was the single point that followed both lines going from the pivot to the center of gravity where the force acts to the direction of gravity. So we now know that the center of gravity is right there. Now what we need to do is we need to hold up our state of Texas mirror here, and we need to put the support directly, when we get this leveled horizontally, we're going to make the support be so it's directly above that point right there. So we can put the support right here if we wanted to. As long as we first we make sure this is level the way we want it, and then when it's level, we make sure that the support is directly above it. We'll use a little plumb bob. That's going to take some time to do. It might be kind of boring to watch, so we're going to stop the video now, and we'll start it up again once we get that added. The first thing we needed to do was to orient the sculpture so it would be in the position it will be in when it hangs on the wall. So we sat in a chair and then used the level to make sure that the horizontal portion of the panhandle on the sculpture was indeed horizontal. Then we moved the level So we could use the level to find the straight line that goes straight up and down from the intersection that we identified as the center of mass. Finally, my wife attached this sawtooth hanging bracket so that the middle indentation on the bracket was aligned with that line that goes straight down to the center of mass. Okay, so now we have the bracket attached up here, and the middle gap, this is one of those little sawtooth brackets, the middle gap is directly in line with what we identified as the center of gravity. And so we could hang it on the wall, but you wouldn't be sure if I was actually, hang it where I said we should hang it. So we're going to hang it here just in front of me. I have a little nail here, and we're going to hold it up at that point. You hold it up at that point, and then if we have done our job correctly, the sculpture should be more or less straight up and down with the panhandle being horizontal up there. Let me show it this way, just get see text the way you're more used to seeing it. And now we see it's supported at that one point, then the texas is horizontal. I mean, the top part of the panhandle is horizontal, which is exactly what we wanted. So now we can hang this up somewhere and have a lovely piece of art that'll make my wife happy.